Okay, thank you very much for joining me today. I'm very excited to talk to you about LiDAR technology. As mentioned, it is the elephant in the room because I think it's one of the last great unexplored sensing modalities with autonomous driving sensors. What I'm here to talk to you about is Velodyne is not a data science company by any means. We just stream the data. But I think we have a compelling reason why we think LiDAR is here to stay, and it's only going to become more ubiquitous over the next few years. So right now, I think mining LiDAR data is definitely a very much an open field in which many of you developers can explore. First, a little bit about us. We started in 1983, so one of the oldest startup companies in the Silicon Valley. We just went through our first round of funding late last year. We started with Velodyne subwoofers. Some of you may be familiar with that. We were the first distortion-free subwoofers using digital signal processing to process information from the cones 16,000 times per second, feeding back into servos to reduce distortion in the speakers. Our CEO is sort of an engineering polymath, and so his interests varied from a wide variety of fields, including mechatronics. So he entered a contest called Robot Wars. Some of you might remember that. These were gladiator robots. We entered with a product called Drillzilla. And you can see the drill in the front would drill into the competition. And we did actually finish in second place, this little 100-person subwoofer company out in Morgan Hill. So you combine digital signal processing, mechatronics. So what is the next challenge for a company like that? The ultimate robot. The DARPA Grand Challenges, robot cars. And Velodyne, again, did an entry into that against universities and some corporate interests, and we finished third worldwide, which was great. The problem with that was we only had 6 miles that we went through the course before we failed. But that was a very interesting competition for us because it informed our approach to self-driving and what we felt the necessary sensing was to make a car drive by itself. And after that, we came out with our high-definition 3D LiDAR. Which you see on the bottom photo there. And we entered that for the second DARPA challenge and finally became just a supplier by the time of the DARPA Urban Challenge in 2007. So what lessons did we learn after that first DARPA challenge? We entered with stereo cameras, and the problem with stereo cameras are pretty much well known today. At that time, though, we discovered that, yeah, ambient lighting conditions were very important. And when you depend on light all the time, you sometimes can result in failures in darkness, low-angle sunlight, shadows. The other thing we learned in self-driving is that we needed very fast update rate, very high-resolution sensing, and maximum horizontal field of view, ideally 360 degrees around the vehicle. All of these things are not unique to robotics, but they become particularly critical when you're talking about a high-speed robotic system like a car. Another key point we wanted to be sure of is we couldn't have false positives. We couldn't just be guessing about what was out there. We need to measure what was out there. False positives in the early DARPA challenges were the reasons why you saw cars moving a few feet and stopping, moving a few feet and stopping. So what we came up with in that second DARPA challenge was not particularly high-tech. It was a very simple and elegant approach, but the implementation was the challenge there. So essentially, we took a typical 2D rangefinder, not much different than this laser pointer here, except we put a detector mated to it so you could measure the time of flight to see how far away an object is based on the speed of light. But Velodyne's IP covers 2 areas primarily. The first is the multiple channels doing that, all in sequence, very short time windows, nanoseconds really, that the detector is listening for the laser signal. Also rotating 360 degrees. So combining those 2 things, we were able to create an instantaneous 3D CAD model of the environment around the vehicle. And when I say instantaneous, if you think of a blink of an eye, a few hundred milliseconds, in that time, we're measuring and firing sensors, or firing lasers at 400,000 times in that blink of an eye. So you can imagine how quickly we can create a 3D point cloud with our technology. So, and this is kind of an example of how quickly you can build up 3D information around the environment. This is how a typical map is made. All of these mapping companies that you see out there right now doing high definition maps. This is just pure LiDAR data stitched together in a technique called SLAM. And you can see at the end you have a product there that's a 3D map. So this can be done in real time pretty much with a Velodyne sensor because of the amount of data that we'd stream. So what was the result of all of these technologies that we brought to the fore? 2007 DARPA Urban Challenge, which was the first demonstration of urban driving. The Velodyne sensor was featured on the top 2 vehicles. And it's mentioned here that it's Stanford and Carnegie Mellon, pretty much the incubators for a lot of what you see today in level 4 and level 5 driving. Both of those programs fed directly into the Google self-driving program that, recently Uber purchased more or less the Carnegie Mellon robotics program as well. So how does 3D LiDAR enable automated driving? What are the key things that we do that other sensors can't? Well, let's start with taking a look at what other sensors do, what the performance of other sensors are. This is Car and Driver report from early last year, monitoring how well cars could detect lane markers. So a very simple part of the whole self-driving problem, just lane finding, lane keeping. And this is the best that cameras could do as of 2016. So in a 50-kilometer course, the red numbers show you how many times the system disengaged because it couldn't find the lines. And this was a course that was around Ann Arbor, Michigan. By far the best performer is the Tesla vehicle, still probably the best level 2 self-driving car out there by far. And within 50 kilometers, 26 times, the system had to disengage because it couldn't read the lines. The Infinity was as bad as 93 times within a 50-kilometer course. So obviously not good enough for a full level 4 driving. It can't even handle the simple task of lane keeping. Some other examples of the camera challenge. You can see the ambient lighting here. That's what we found in the first DARPA challenge. Very clearly, you're not going to be able to pull much data out of something like this. Similarly, very complicated scenes that are rapidly evolving and changing. You get something like this, way too much data to be parsed and to figure out what's going on in that scene. An example of a radar challenge is right here. Radar is a relatively low-resolution sensing modality. So if you look at that bridge that's going over the road there, it really can't tell where that is in the Z-plane. Is it a wall right in front of the car? Is it a bridge over the vehicle? So these are some of the problems that you see with other sensing. In fact, something like this is exactly what happened in the Tesla accident last year. So how does LiDAR perform a little bit better in those situations? This is an example of lane keeping. Cameras, as I mentioned, haven't really proven their reliability. And we feel that with LiDAR, it becomes a much more robust system, being able to detect lanes. So our sensor gives you 2 pieces of information. It gives you a position in space, and it gives you a reflectivity. So with lane markings, they have a higher reflectivity than the asphalt around it. So you very clearly can see those popping up. And if you're looking at the image on the right, lower right hand, that purplish image, you can see the lane markings. They have a much greater reflectivity, and they stand right out. Also for 3D non-painted markers, like bots, dots, those kinds of things. Again, you have additional spatial resolution that you can determine the location in space of things like that. Another situation, poor ambient lighting. This is raw data from a Velodyne LiDAR. Not quite a video image, but it's pretty high resolution stuff if you take a look at it. The different colors represent different reflectivity as objects that we're hitting. And you can see this is kind of like the Tesla incident, if you will. You can see that truck drive right by. And of course, what the advantage of LiDAR data is it's 3D data. So you can look at it from any perspective. And you can see the very bright retroreflective. The red stuff that you see on this are retroreflective objects, so like the back of the truck that would be very reflective, lane markings. Another use case for autonomous driving, level 4, level 5, then I should point out this is one area that even the Volvo isn't doing with their Gothenburg trials, is merging onto an on-ramp, onto a freeway. Again, you need a very high horizontal field of view sensor to be able to do something like this, and you need to have very high resolution spatially to be able to determine where in space the other vehicles are. And there are no other sensors out there that are able to tell you exactly where other cars are when you're trying to merge with them. It's a very dangerous maneuver for cameras or radar. Something that we have a lot of in the United States are these skewed intersections where you'll come up to a highway road and you'll need to make a left turn onto it. And the cross traffic might be moving, 45, 50, 60 miles per hour. And you need to be able to slowly pull out and make a left turn onto something like that without getting into an accident. And so you need something, again, with a 360-degree view around the vehicle, and you need to have a very long range, high spatial resolution view of that. So if you're looking at the right image, that's raw LiDAR data, and that's a LiDAR that we've made that sees 200 meters. And so you can see, if you carefully look, you can slowly track, or you can carefully track the little cars that are moving in and out of that scene. And you have an exact XYZ position of every car in that frame. Encroachment, lane encroachment. Radar has a problem with these sorts of situations. It's very noisy. You need a lot of filtering on it. And you can't really detect the signal and the noise in something like this. The image on the right, you'll be lucky if you do get a flag on the back of a load like that. But again, this is something that LiDAR can see pretty well in 3D space. Example of unmapped objects for self-driving, road debris. So anything standing above the ground plane. That's something that LiDAR, again, will be measuring. So a camera will kind of estimate what's out there, whereas a LiDAR is actually measuring. So something like this, or a depression below the ground, let's say a pothole, like we have a lot of these days in the Bay Area. These are the kinds of things that a LiDAR might be able to help you detect a lot better. And this is probably an area that's pretty ripe for machine learning. So that said, I've just kind of sold you on how great LiDAR performs in this space. How does it actually perform? We have a couple of data points. We have the state of California 2015 and 2016 results. These here show the 2015 results of self-driving cars that are licensed in the state of California. The y-axis here shows the number of kilometers between disengagements. In other words, how far the car drives before the human driver has to take over because of some error. And there really is no contest. If you looked at it last year, Google was driving almost 2,000 kilometers between times the driver had to take control. Most of the other companies, I think, were at least an order of magnitude less than that, 40, 50 kilometers at best. Some of them were as low as less than 1 kilometer. And I think one of the key differentiators between those two, besides the experience of Google, which is indeed vast, is the fact that Google was the only one there using a high-definition 3D LiDAR point cloud. So they had that advantage over the other competitors at the time. At the time, in 2015, none of those were using anything more than a 2D LiDAR. But is it just Google's experience that makes them drive so well? So we take a look at the 2016 L4 performance. I chose to take a look at this data a little bit differently than the previous years. On the y-axis here, I've put a measure of driving complexity. So the least complex situation would be just kind of a highway autopilot sort of thing. Maybe no lane changing even. Just a very simple adaptive cruise control, lane keeping type of application. That would be the least complex of driving situation. The most complex would be driving here in the city of San Francisco. And what we found from the data this year, if we kind of read through all of the reports, is that there was one company that actually exceeded Google in terms of the complexity of situations it was trying to drive in, and that was cruise automation. And I'm sure a lot of you have heard of Cruise Automation. It's a company that had a relatively short history in the self-driving space. In fact, none of the folks there were from the DARPA challenges, and so they kind of jumped right into the space, and people were wondering, why did GM pay $1 billion for this company last year? Well, this is one of the reasons why. Suddenly, GM has catapulted themselves into driving in the most complex situations. And if you've tracked the Cruise data over the last year, you can see early in the year they were like a few kilometers between disengagements, and towards the end of the year there were well over 100, maybe a couple hundred kilometers between disengagements. So Cruise made huge leaps in it without a long history in self-driving. And I'd like to think that part of that was hardware related. If you look at the internet pictures of Cruise, they've got a couple of very obvious high-definition LiDAR sensors on top of the vehicle. So, you know, this kind of begs the question, is it all AI, or, you know, is it a matter of what kind of hardware sensing suite you have on the vehicle that ensures your success? Cruise automation performed quite well, though, by jumping into high-definition LiDAR, we feel. This is just some other data. Just again, I'm trying to impress upon you the fact that the market is changing and LiDAR is here to stay, and it's just going to grow. When I started at Velodyne a couple of years ago, which makes me the old guy at Velodyne, 2015, there was only one company among the automotive OEMs, traditional OEMs, that considered using high-definition LiDAR for level 4 driving. That was from press releases, everyone knows it's Ford. And they were the only one. Everyone else said, yeah, we can use it with low-definition LiDAR, and the majority, in fact, felt that LiDAR wasn't even necessary to tackle the problem. Vision was plenty of data. Vision and radar would be plenty. And at that time, Ford was probably asking themselves, you know, are we crazy, or why are the only ones using this expensive sensor right now? You know, are we not seeing something that the rest of the market is able to see? But just the opposite happened. The rest of the market kind of came around to Ford's way of thinking. So in 2016, almost half of the companies out there, a third of the companies out there were using high-definition LiDAR, decided that that was the way they needed to pursue level 4 driving, level 4 and above driving. And today, there's only one company left among the OEMs that I'm aware of that feels that LiDAR is not necessary at all for full level 4 driving. So the market has definitely come around to this way of thinking, and I think it leaves a lot of opportunities for people who are looking to perform machine learning on LiDAR data. If we take a look at also the acceptance of LiDAR data among the non-traditional automakers, I think across the board, everyone is using high-definition LiDAR. I can't think of a company that is pursuing level 4 and level 5 without it. And you've seen pictures of all of these companies in the news. A lot of these are confidential now. They become confidential as we go, so pretty soon the whole thing will be confidential. But all of these photos are available on the internet. So where is LiDAR going to go next to ensure that it indeed becomes a sensor on every single car made out there? The keys that we need to accomplish at Velodyne are maintain the range and resolution. So the very large sensor that you see on top of the old Google cars, the HDL64 Velodyne, we need to maintain that resolution. And if anything, we need to improve upon that. And so this year, Velodyne has announced that we've developed a sensor that sees twice as far as our previous generation of sensors. Instead of 100 meters, now we're at 200 meters. And so we're slowly climbing up that bridge to be able to get to high-speed driving at level 4. Of course, because they're going to be put into cars, form factor is a concern. That first sensor I showed you at the beginning was about a 1-meter diameter sensor on top of the vehicle, obviously not very practical. And today our smallest sensor is about 100 millimeters in diameter. Being automotive, weight is very important as well. We've gone from about a 30-kilogram sensor to an 800-gram sensor today with 32 channels. And cost. I've heard, I think, my friend Wolfgang mentioned that we would be below $250. I'd say, please hold off one moment, give us a little more time. But we have publicly announced that we think it's just a matter of time before we get to a $500 sensor or below. Our CEO likes to say that this sensor is just a bag of electronics. You make enough of them, and the price will come down. Kind of give you an idea of the scale of what Velodyne has done. We are the biggest player in this space of self-driving, but up until 2015, we probably sold a couple of hundred sensors into the automotive space per year. So 200 sensors. And so when we're talking about millions of sensors, obviously there's a lot of opportunity to bring that $85,000 cost down by orders of magnitude. And of course, probably the key driver behind all of this to make sure that it gets introduced into cars is automotive durability. This will be quite a challenge, but Velodyne, again, 10 years working more or less the same space. You know, our technology, even our solid state approaches are going to be one laser, one detector, collinearly aligned, multiples of them. It's just a matter of how inexpensively we can make each of those channels that will get us the lower cost. But the automotive durability, we're pursuing along the same technology path that we have for 10 years. And so we've got a lot of experience in the field. That picture of the truck there are those autonomous dump trucks that have been driving in Australia for about 5 years. They have a very high duty cycle. They don't take many breaks. They run more or less around the clock. They get shot with fire hoses daily. You can see it's a very dusty environment, iron ore mines. And so we do have some history in trying to ruggedize this sensor. And so we think we're going along the right path as we proceed. And so this year we've introduced to some of our select automotive OEM customers the VLP32 sensor. We like to think that that fundamental architecture will be the one that we're going to see in millions by 2020, 2021, that time frame. So we think there is definitely a path to getting LiDAR sensors on every vehicle, but it's just a space that not a lot of machine learning has been focused on, you know, getting XYZ data plus reflectivity. How does that feed into your algorithms? I've put together, just off the top of my head, again, we're not the ones coming up with these needs, but these are kinds of things I've seen from some of our customers. One of the advantages I have at Velodyne is because we're kind of in the lead right now. We get kind of a crowdsourced information from customers about what their needs are in the marketplace. I kind of put into 3 general categories here, but some of the more focused tasks that I think self-driving companies are pursuing are pothole detection. That's more of an ADAS application, but high-definition LiDARs, you know, I would imagine would probably be the best possible way to go about this. Finding a hole beneath the ground plane. I mean, that's exactly the kind of information that we send to you. Also, we provide reflectivity, so there may be some information in that can be mined. Road debris, I mentioned that tire carcass earlier on. Again, that's another thing that I think is probably ripe for more machine learning work to be done. 3-dimensional lane markings, reflectors that pop up. Remember, we have reflectivities as well, so we see reflective items very, very well in any kind of lighting. And also, being a 3-dimensional marker, we see that as well. So there are a lot of opportunities, we think, for focused tasks to identify 3D objects in the environment. Some of the more broader LiDAR-based tasks, localization, finding your place where you are within a map, object identification algorithms, perhaps that's, I think a lot of the literature points to LiDAR plus camera in that. Segmentation of the environment, that's one that's traditionally been done for LiDAR data from aerial applications like forestry and things like that. I just got kind of an example here of segmentation. This is just segmentation with pure LiDAR data. So what they've done with SLAM here is they've identified the ground plane, they've identified the road surface. With our reflectivity measurements, you can see the lines in the road, the lane markers and the crosswalks, and you see the stuff above the ground plane, the trees and whatnot. And all of this is done with pure LiDAR data, not using any kind of machine learning or artificial intelligence of any kind. So you can imagine a lot of this could probably be cleaned up as it is from aerial mapping with machine learning. Also, I think another opportunity for you developers would be the artificial intelligence infrastructure to support LiDAR for self-driving. Right now, data itself is something that doesn't exist out there. There's not much LiDAR data available because, again, if you think about it, there was Google and there was Ford for many years that were driving around collecting data, and even they aren't collecting it on a massive scale. They're collecting data, you know, a few cars at a time here and there over a few miles. So whoever owns that data, I'm not sure who those companies are going to be in the future, but if you have access to LiDAR on a lot of vehicles, you're going to have a huge advantage in the self-driving wars. Also, scalable and accurate data labeling seems to be a challenge. A lot of our customers are, in fact, all of them pretty much do it the same way. They have very manpower-intensive labeling methodologies that are very cumbersome, not necessarily accurate, and they probably aren't scalable for the massive amounts of data they're going to want to process in the future. So I think there's probably an opportunity for companies looking into this space as well. So I think that's about all I've got time for today, but thank you very much. Any questions?
might be an uninformed question, but I wonder why there isn't enough LiDAR data. Does it have to be on a self-driving car, or could we just have those sensors on every car and collect road data?
Yeah, there's just not that many LiDAR sensors out there right now that are, I should say, 3D high-definition LiDAR sensors. You know, we have a lot of those very short single-line sensors for emergency braking that have been on the market for about 10 years, but really that's not LiDAR data per se. This level of data, again, I mentioned we made for cars 200 just a couple of years ago. You know, even today we're only making them in the thousands, so there's not a lot of people collecting this data. There's a lot of aerial data collected that might be of use, though. Thank you very much.
You mentioned one car company is not relying on LiDAR, and right here.
Oh, there you go.
So what are they using instead, and how do they perform? And maybe can you include the name?
Yeah, I mean, I think Elon Musk has made it very clear he doesn't want LiDAR on his vehicles, and you can look at the California DMV this year is probably the best indication of what they're doing for level 4 driving, and they're not trying the most challenging situations, and they're you know, if you look at the data, I think it was once every few miles they're having to disengage. I mean, we saw the one very bad example of what happened last year when the white truck crossed their path, and the white truck with a low-angle sunlight background was not visible by the camera. And to the radar, could have been could have been a bridge over the road. It could have been anything. So, yeah, LiDAR gives it that three-dimensional aspect that you don't have.
I'm going to do one more question. Anyone else? Okay. All right. Well, thank you very much.
Thank you.